Okay, so topic is hyperconjugation, inductive effect and resonance effect we have already done.
Yes, sir.
So hyperconjugation, as the name suggests, means there is conjugation but at extreme. Hyper or hypo, hyper means extreme, very large. So hyperconjugation, what it means, that there is, whenever we have carbon hydrogen bond in conjugation with carbon carbon double bond, this is the first case. Then you will look at the resonance. See, saturated carbon, means carbon which has only sigma bonds and it is sp3 hybridized. So, and that saturated carbon has hydrogen atoms
Yes, sir.
attached to it. So, this is called alpha carbon.
Yes.
Saturated carbon next to the carbon carbon double bond is called alpha carbon, and hydrogen attached to it are called alpha hydrogens. So what happened when we have such arrangement? Carbon hydrogen sigma bond form double bond, and pi double bond means pi bond shift next, means overall this is called delocalization of a double bond, and this hydrogen is in the form of H plus ion, but it remains at the same distance as in the bonded state. See, there is no, it seems like there is no bond between carbon and hydrogen, but it remains at the same distance as in the bonded state. So that's why it is called no bond resonance. Hyperconjugation is also known as no bond resonance. So above all, what happened because of this conjugation? There is delocalization of pi electrons.
Yes.
Just like in case of a resonance. But in resonance, there is delocalization due to the presence of lone pair or more pi bond on more electronegative atom likewise. So resonance is dominating over hyperconjugation, means if okay, and second thing, hyperconjugation is always electron releasing effect. Hyperconjugation is always an electron releasing effect. That means more the number of alpha hydrogens, more is the delocalization of pi bonds, and more is the stability of alkene. So that means
More
hyperconjugation.
number of hydrogens around the double bond system will contribute to stability of alkene.
Yes, means
Okay.
carbon on saturated hydrogens on saturated carbon next to the double bond, then that contribute to the hyperconjugation, and that is called no bond resonance, and it is also known as sigma pi conjugation. Because CH sigma bond is in conjugation with pi bond. So this is also called sigma pi conjugation. At the same time, if there is a CH sigma bond adjacent to positive charge, means when we have carbocation. So carbocation is electron deficient. So obviously electron releasing groups will decrease its electron deficiency and increase its stability. See, in this case what happened, because positive charge means electron deficiency, so this sigma bond turns into pi bond. Okay, and one more thing, why is it remains at the same distance as in the bonded state? Reason being, it is not totally free. See, when we have a pi bond, obviously there is pi bond like this, and this is sp3 hybridized.
Yes.
So this bond is like this. So this sp3 hybridized at bond, and these two p orbitals, they overlap simultaneously with each other. So that's why it remains at the same distance as in the bonded state, because it is not totally free from the carbon. That's why this H plus is written without any bond between carbon and hydrogen, but it is connected with this pi bond. So it is always in means in bond almost in bonded state. It is partial double bond character is formed.
Okay.
So let us say we have ethene and propene. So out of ethene and propene, which one is more stable?
Propene, sir.
So out of ethene and propene, propene is more stable because there are 3 alpha hydrogens. 3 alpha hydrogens means 3 hyper conjugated structures. 3 hyper conjugated structures means more delocalization of
Pi.
yes pi electrons. So increase the stability.
So, but there's only one pi bond and there are 3 alpha hydrogens. So, how will each one of them cause delocalization of pi electrons?
See, when we have 3 alpha hydrogens, so first of all, one alpha hydrogen will show conjugation. Same, second will also show conjugation, and third will, so instead of, it will increase the delocalization, means delocalization is increased 3 times. If there is only one hydrogen, instead of one there are 3, so there are 3 hyperconjugated structures. So more the number of hyperconjugated structures, more is the delocalization of pi bond, and therefore more is the stability. So in simple words, as number of alpha hydrogens around positively charged or around double bond increases, the stability of the alkene increases.
Okay.
Now first one was ethene, second is propene, and let us say third is butene. So obviously in this case there are 3 alpha hydrogens, and
Yes.
and in this case in butene,
6.
so in butene there are 6 alpha hydrogens. So stability of butene is further increased. Now in butene, it has geometrical isomerism. What is the condition of geometrical isomerism? First, it should have carbon-carbon double bond and 2 atoms or groups attached on the double bonded carbon should be different. So this is called cis alkene.
Yes.
And this one is called
Trans.
transalkene.
Trans form is more stable, right?
So transalkene is more stable. Now see, alpha hydrogens are equal, so hyperconjugation will not decide which alkene is more stable. So in this case, steric hindrance will decide.
Yes.
In trans, steric hindrance is less because bulky groups are attached on opposite side, but in cis alkene, steric hindrance is more because bulky groups are attached on the same side.
Yes.
And if we have this alkene, so tell me, in this case, see there are 9 alpha hydrogens. There are 12 alpha hydrogens. So obviously the alkene with 12 alpha hydrogens are more stable than with the 9 alpha hydrogens.
Yes.
So in this way, as the number of alpha hydrogens increases, stability of the alkene increases. Same is the case in case of stability of carbocation. So in carbocation, alpha hydrogen is one which is attached to the saturated carbon next to the positively charged carbon. So this is positively charged carbon.
Yes.
If it is attached to only hydrogens, so we can say there is no alpha hydrogen.
Yes.
In this case, how many alpha hydrogens are there?
3.
So there are 3 alpha hydrogens. In this case, there are 6 alpha hydrogens.
Yes.
And there are 9 alpha hydrogens.
Okay, so this is why 3-degree carbocation is more stable.
Yes, methyl, ethyl. This is called isopropyl,
Tertiary butyl.
and tertiary butyl. So tertiary butyl is more stable than isopropyl, which in turn more stable than ethyl, which in turn more stable than. So more is the number of alpha hydrogens, greater is the delocalization of positive charge.
Understood.
Delocalization means there is a decrease in positive charge
Yes.
due to the movement of positive charge from carbon to hydrogen. See, this was positive charge. These are the hydrogens. So positive charge that move from carbon to hydrogen. So in this way, more the number of hydrogens, alpha hydrogens, more is the delocalization of positive charge, means appearance of positive charge of the carbon decreases, and in this way it increases the stability of the carbocation. Same stability of free radical. Free radical means having odd electron. Carbon having one unpaired electron. So this is methyl free radical. It is neutral. Now you know carbon has 4 electrons. Out of 4 electrons, 3 are shared with other atoms or groups, and 1 electron left unshared. So it is actually electron deficient species. So again same, this is 3 degree, 2 degree, 1 degree, special case of 1 degree, that is methyl. So stability order is same. Now how this delocalization takes place in free radical? This is odd electron.
Yes.
So it is like this. This is called half-headed arrow or fish hook arrow, where each see, this carbon has 1 electron in the bond, hydrogen has 1, so each one will take its own share back. That is it. So there is delocalization of the free radical, and therefore more is the number of alpha hydrogens, more is the delocalization.
Okay.
So again, stability can be explained. So Huckel rule I will explain once more.
The 4n plus 2 pi electron rule, sir.
So a compound is aromatic when it satisfies the following conditions. So first condition is it should be cyclic.
Yes, sir.
Second,
It should be plain.
it should be planar.
The carbons should be sp2 hybridized.
All the carbon sp2 hybridized. There is delocalization of pi electrons, and number of pi electrons is equal to 4n plus 2.
2 pi.
N may be 0, 1, 2, 3 and so on. And if
Instead of 4n plus 2, there are 4n. and
number of pi electrons is equal to 4n pi, then it is anti-aromatic. If any one condition is not satisfied, the
compound is then non-aromatic.
compound is non-aromatic. So let us solve some questions related to order of stability. So aromatic compounds are most stable
Yes.
and anti-aromatic compounds are least stable.
Okay.
This is the order. Aromatic most stable, then non-aromatic, and then anti-aromatic. Okay. So now let us solve few questions. Okay, hyperconjugation is also called Baker-Nathan effect,
Okay.
because why hyperconjugation is called Baker-Nathan effect? Because they were discovered by Baker and Nathan.
Okay.
one more name is given to hyperconjugation, that is Baker-Nathan effect, or